In November 2012, NASA astronomers observed a new galaxy named MACS 0647JD. This galaxy, despite being smaller than the Milky Way, was one of the most intriguing we have ever discovered and was only revealed thanks to an amazing natural phenomenon. The galaxy was picked up using NASA's Hubble telescope and also the Spitzer telescope, but was only made possible by a phenomenon known as gravitational lensing. This occurs when the photons emitted from a luminous object are bent and warped by the gravity of a massive object, usually a galaxy. In this case, however, MACS's light was magnified by not just an intercepting galaxy, but by an entire galaxy supercluster. As such, as of the making of this video, MACS 0647JD remains the farthest galaxy we have ever observed. With an estimated distance of about 13.3 billion light-years from Earth, it verges on the very edge of the universe. Or does it? We live in a vast open dimension with an estimated age of just under 14 billion years old. We know this because the oldest visible light we have ever observed is around this age. The furthest light we can see in the universe makes up the boundaries of what we perceive as the observable universe. Even if the universe was expanding at the speed of light, the observable universe should only have a maximum diameter of just under 28 billion light-years based on its age. And yet, given our estimations of redshift, it seems as if our own observable universe is as voluminous as to be over 3 times that size, at around 93 billion light-years in diameter. What lies at the edge of, or indeed beyond, the convoluted boundaries of this observable universe is still a mystery, but there's an even bigger one lurking beyond the twilight curtain. Thanks to our redshift analysis, we know that some galaxies, including MACS 0647JD, are receding away from us at a rate faster than the speed of light. While their oldest light is still being emitted and is only just reaching us, we now know that these galaxies have since disappeared over the cosmic horizon, and these parts of space will never be reachable again. But how can this be? Why has the universe expanded faster than the speed of light? Why are distant galaxies receding away from us in the first place? And furthermore, why are they speeding up as they go to beyond light speed velocities? It's not impossible to look out at the night sky and wonder, why are so many facts of astrophysics seemingly challenged when we begin to look towards the edge of the void? The so-called observable universe is a spherical region independent to the structure of the entire universe, which encapsulates all the light and matter that is observable to us here on Earth. The observable universe has become synonymous with our study of the cosmos, but every point in space has its own arbitrary observable universe. As such, there is a barrier when, once crossed, things are no longer visible to any particular point, as light has not had enough time to reach that area. This boundary is known as the cosmic event horizon. Our observable universe grows at the speed of light, so any anomaly disappearing over the cosmic horizon would, hypothetically speaking, need to move faster than light in order to escape from our field of view. This should be impossible, according to special relativity, and yet this is exactly what as many as an estimated 96.4% of all galaxies we have ever observed have already done. The light reaching us now is essentially illuminating a galactic hologram. Although a constant visible stream of protons is a sure thing for billions of years to come, those galaxies in question are now physically unreachable to us by any known methods of travel according to special relativity. But their older light will serve as a sort of replay for their past. Looking towards the edge of the observable universe for this early light is actually very useful to us here on Earth, providing a clear glass pane into the distant past of our universe. Not only has this helped us to determine its estimated age, but we've also been able to piece together its life cycle by looking back through the various stages of its development. We often see black holes swirling gas on their accretion disks to create quasars in the earliest reaches of the historic light. We also see young galaxies and a much more volatile and unpredictable universe in general. Our observable universe is estimated to be 93 billion light-years in diameter, but the farthest objects we have ever observed before the cosmic horizon seem to sit at about 46 billion light-years into the void. So why is this? Why are we still left with this unanswered question? How can the observable universe be larger than the age of the universe multiplied by the distance travelled by the light within? Well, it's a difficult idea to consider. When looking up at the stars in our own galaxy, there is always a consistent latency that never changes. The light being emitted from our neighbouring star, Proxima Centauri, takes around 4 years to reach us, and that is a consistent delay that doesn't change. But with extragalactic observations, there is no consistent latency. Our universe is expanding at different rates based on what it has been through: matter, neutrinos, radiation, etc. And we are moving through space too. As such, the light emitted from an object worlds very close to us, such as the early formation of the MACS galaxy, once faced an intergalactic journey across ever-expanding space to reach our eyes some 13 billion years on. We now estimate that this galaxy and many other objects at the edge of the observable universe to be as far as 46 billion light-years away, and its light would never possibly reach us now, having passed the boundary in which light's speed and the universe's age no longer cooperate. Beyond this barrier, the universe becomes causally disconnected from the observable universe, in other words, segmented, detached, fragmented, and divided. This explains why MACS 0647JD appears to be so young and small for such a seemingly old galaxy. It formed very soon after the universe's creation, a few 100 million years after the Big Bang, hypothetically, but the light it is emitting has been on an absolutely enormous intergalactic journey. This observed phenomenon of increased speed of expansion could potentially mean there may be up to 2 trillion galaxies for us to observe in the future, as opposed to the several hundred billion excess we used to believe. In the future, our observable universe is expected to grow and our field of view is expected to extend. But keep in mind that there is a clear disparity between the observable universe and what we know as the reachable universe. The reachable universe is what you'd expect, the area before the cosmic horizon, where we could still reach distant interstellar and perhaps intergalactic objects given enough time. Beyond the cosmic horizon, well, nobody really knows what lies beyond it. We don't know what actually happens to galaxies once they pass over. While we presume that it is just more of the same, stars, galaxies, planets, and black holes, we do not know if there is anything beyond, and that is not just a massive void or a physical edge. But it is a likely scenario that more of the same does exist beyond the boundary, and if you thought a 93 billion light-year spanning observable universe was vast, no man's land will blow your mind away. At 93 billion light-years, the observable universe can seem almost incomprehensibly large, but then you realise that its entire expanse barely even scratches the surface of the total isolated universe beyond the barrier. While we never know for sure, it is very likely that the expanse beyond the cosmic horizon could be hundreds, thousands, or even million times larger than the observable universe. But the question is how? The universe should not be anywhere near this large. In fact, when it was approaching the halfway point of its life so far, we think it may have even started to slow down in its expansion. The current estimated rate of expansion of the universe is about 68 kilometers per second per megaparsec. This is not a sphere expanding uniformly either. This is empty space being elongated in every direction thanks to unknown natural forces. Though the universe is expanding by 68 kilometers a second, this is per megaparsec. A megaparsec is a unit of distance equivalent to about 3.26 million light-years. So for every 3.26 million light-years further away from us you travel, the faster the universe appears to be expanding. For example, just over 6 million light-years from Earth, the universe is expanding at about 204 kilometers per second from our perspective. At intergalactic distances, the speed of recession reaches extremely high velocities, eventually reaching a distance at which it supersedes the speed of light. The laws of special relativity say that nothing can move faster than the speed of light, of course, but special relativity is a local domain. Right now, you can't personally jump onto a spaceship and move faster than light, but when comparing and contrasting intergalactic distances from one another, this restriction becomes a lot less clear-cut. The metric itself is not ruled out. But that is just the apparent speed of the galaxy's receding. We still haven't covered why space itself is expanding faster than light, and why the universe is so much unimaginably bigger than the expected dimensions. Well, it was through the receding galaxies that this question was asked in 1998, and it prompted the High Z Supernova Search Team, of whom 3 of the members won Nobel Prizes, to research this. They concluded that the universe had experienced the vast majority of its unsolicited growth in the second half of its life. Before this, the universe's expansion was actually believed to be slowing down due to the gravity of large objects from within. Before a stage in the universe's life known as the dark energy dominated era began about 6 billion years ago. Dark energy is a fascinating concept we know very little about. You've probably heard of the terms dark energy and dark matter used synonymously, but whereas dark matter is a form of matter that could constitute some kind of undiscovered particle, dark energy is a form of unknown energy that exists within the vast, empty swathes of the universe. With the theory of general relativity, the accelerated expansion of the universe can be explained by a positive value within the cosmological constant, an equation proposed by Alfred Einstein to determine the energy density of space. This positive presence can also be described as vacuum energy, or by its better known term of dark energy. Though we never have observed it, we have seen light distorted by the aforementioned phenomenon of gravitational lensing in seemingly empty areas. This suggests that dark energy doesn't seem to interact with normal baryonic matter that we know of, and only seems to be influenced by gravity. Dark energy may not even be a physical presence per se either, and could just be a property of the universe's emptiness, but failing that, it is believed to be highly homogeneous and has a low density. Dark energy is evidenced by the need for an additional type of energy that is not matter or dark matter, given that the universe appears to have expanded more in the latter half of its life. Principally, something must be driving this faster-than-light expansion. Large-scale mass density wave patterns also lend credibility to dark energy's existence. But that tells us nothing about why it exists. Why is it pushing space apart? Why is it moving faster than light? Why is it only present in the darkness? We only know mathematical equations that allow us to guess at its nature, but assuming the current models of cosmology are correct, dark energy is estimated to account for as much as 2/3 of the entirety of energy within the observable universe, notwithstanding the rest of it. Now compare that to a 27% share of dark matter and a mere 5% of the matter that we already know and understand. Haunting questions aside, if dark energy is driving the universe's aggressive expansion beyond the speed of light, then how big is it? Not just the observable universe, but the total universe. Well, there are many conflicting theories and ideas, and a range of estimated values out there. One theory actually contradicts the idea of a larger, unobservable universe, stating that the universe may only be about 78 billion light years in diameter. Neil Cornish et al. Released a paper stating that the universe may actually only be 98.5% of the expected range of the cosmic microwave background radiation map, but his tests on the CMB failed to find any evidence of finite boundaries at such a distance. Even then, some people still believe that the observable universe may be the total size or even larger than its entirety. Why do we see galaxies beyond the estimated size? Well, it has been argued that these could well be reflections. If the universe curves on itself, then photons could hypothetically circumnavigate with the gravity at the edge of the universe, and with hundreds of billions of distant galaxies in the observable universe, we'd have no way of ever matching a galaxy to a possible reflection, and no way of ever knowing if we'd found an authentic galaxy. That being said, there are many more lines of proof to contradict these theories than prove them. Other estimates range from between the 156 billion light years to 180 billion, incorrectly inferred from the 78 billion figure that was misconstrued as a radius, not a diameter. A more rigorous method of testing would be to measure the positive and negative curvature of what we believe to be the spatially flat universe. This is just what the Sloan Digital Sky Survey and the Planck satellite aim to do, and concluded that, due to the lack of a defined curvature from the survey space, our observable universe may be as little as 0.25% of the radius of the total universe. No meaningful curvature was detected, and so a vastly larger area would be required for such an expected curve. This equates to a staggering 23 trillion light-year radius, around 15 million times more voluminous than our observable universe's entire expanse. What is scary is that this estimate may actually be quite pessimistic. The real size could significantly be bigger than even 23 trillion light years in radius. If we go all the way up the estimates, we come to the infinite universe theory. Given the sheer size difference and mystery surrounding dark energy, some believe that the total unobservable universe may actually be endless. After all, if it is expanding, then what is on the outside that is independent? It's hard to believe that there is simply nothing outside of an arbitrary boundary. And if the Big Bang truly happened everywhere, then why couldn't it be infinite? As numbers climb and estimates grow larger and larger, more and more people are adopting the theory that the universe outside of what we can observe may actually go on forever. Whatever the case, the expansion of the universe is just a mind-bending concept to grasp. The universe is not technically expanding into anything, and technically no space on the exterior is required for the interior to grow. It truly numbs the mind. Space is incredible, and it may just be hiding yet more weird, wonderful, and even physics-defying properties in its darkness. With over 96% of the galaxies we can currently observe having disappeared over the cosmic horizon, the same fate awaits the vast majority in the distant future. Thanks to dark matter and the period after cosmic inflation, all galaxies from our position are bound to either be drawn to us or to cross the cosmic horizon and be lost forever, with no in between. With the universe's vastness, it's quite anticlimactic to think that even if we successfully develop near light speed travel, the furthest we could ever hope to reach would be the distant minor galaxies of the local group. Cosmic inflation was an event that forced the universe from a minuscule size into an expanding gargantuan cosmic chamber that it's become today, and with it, most matter was flung beyond our reach. Gravity has helped to bring back galaxies like Andromeda and the rest of the local group to within our grasp, but the truth is, that's it. Everything else has escaped our clutches and hence will, in time, cross the cosmic horizon and become causally disconnected and become unreachable forever. The local group is our pocket or segment, and as such, the gravity of all the objects will eventually draw nearby messier objects together into one big super-elliptical galaxy named Milkdromeda. If humanity was to be able to retain the presence and capabilities to observe the skies for billions of years beyond this point, then eventually we will see the observable universe expand by a third, to about 62 billion light years, revealing another 2 trillion galaxies to observe from afar. But soon after, the photonic relays of the foregone galaxies will begin to be redshifted all the way into the microwave and radio wave spectrum, disappearing from view. This is similar to what we believe happens at the event horizon of a black hole, and the oncoming curtain of darkness and nothingness enveloping a visible universe of trillions of galaxies from the outside inwards is an unsettling thought, to say the least. Eventually, the entire observable universe will slowly fade from view, eventually leaving only Milkdromeda, bounding everything within the local group by gravity and excluding everything else. We will be down to our last trillion stars, from our perspective anyway. When our galaxy is left alone completely, then it may become much more accommodating to intelligent life. Most of the early universe hazards that made it such a harsh place will have subsided with the lower density of space. That means that all of the billions of habitable planets left within Milkdromeda will stand a much better chance of producing intelligent life. But by the time any sort of civilization emerges, there will be no other galaxies or anything besides our own in view. They will never be able to observe distant galaxies and will never be able to learn as much about the universe as we have. Perhaps they will practice the belief of the island universe theory, an early belief for Andromeda when it was first discovered. Space will simply become something that stops at the edge of the galaxy, and they will never know that the galaxy is one in an expanse of trillions. Even if they managed to speed off into the unknown at light speed, they would never find anything in the darkness. They'll never have the opportunity to see distant stars, galaxies, megaclusters, black holes, quasars. It will all be too late, and they will never know what they missed. As such, it does seem as if we exist at the perfect time to observe, study and comprehend the universe. We have managed to develop a profound understanding that no civilization in the distant future will ever be able to attain. But, for all we theorize about what lies outside the observable universe, the illusion of galactic solitude in the future does make you wonder, what could we have already missed? What could be the other side of the cosmic horizon right now? How much more would we stand to learn if we could see beyond it? It is these mysteries and theories that make discoveries like MACS 0647 JD so fascinating. One day, observing distant galaxies will be impossible. All this is to come in a vast, lonely and expansive universe.